In this problem, Romeo and Juliet are to meet up for a date, where Romeo arrives at time x and Juliet at time y, where x and y are independent exponential random variables with parameter lambda. And we're interested in knowing the difference between the two times arrivals. We call it z, written as x minus y. And we'd like to know what the distribution of z is, expressed by the probability density function f of z. Now we'll do so by using the so-called convolutional formula that we learned in lecture. Recall that if we have a random variable w, that is the sum of two independent random variables, x plus y. Now, if that's the case, we can write the probability density function, fw, little w, as the following integration, negative infinity to infinity, f of x, little x, times f of y, w minus x, integrated over x. Now to use this expression to calculate f of z, we need to do a little bit more work. Notice w is expressed as a sum of two random variables, whereas z is expressed as a subtraction of y from x, but that's fairly easy to fix. Now we can write z, instead of as a subtraction, write it as addition of x plus negative y. So in the expression, the convolution formula, we'll simply replace y by negative y, as we'll show on the next slide. Using the convolutional formula, we can write f of z, little z, as integration of f of x, little x, and f of negative y, z minus x, dx. Now, we will use the fact that f of negative y, evaluated z minus x, is simply equal to f of y evaluated x minus z. To see why this is true, let's consider, let's say, a discrete random variable y. And now the probability that y, or negative y, is equal to negative 1 is simply the same as the probability that y is equal to 1. And the same is true for probability density functions. With this fact in mind, we can further write equality as the integration of f of x times f of y, x minus z dx. We're now ready to compute. We'll first look at the case where z is less than 0. Now on the right, I'm writing out the distribution of an exponential random variable with the parameter lambda. In this case, using the integration above, we can write it as 0 to infinity lambda e to the negative lambda x times lambda e to the negative lambda x minus z dx. Now the reason we chose a region to integrate from 0 to positive infinity is because anywhere else, as we can verify from the expression of fx right here, that the product of fx times fy here is 0. Okay, follow this through. We'll pull out the constant lambda e to the lambda z, the integral from 0 to infinity lambda e to the negative 2 lambda x dx. And this will give us lambda e to the lambda z minus 1 over 2 e to the negative 2 lambda x infinity minus this expression value at 0. And this will give us lambda over 2 e to the lambda z. So now we have an expression for f of z evaluated at little z when little z is less than 0. Now that we have the distribution of f of z when z is less than 0, we'd like to know what happens when z is greater or equal to 0. Well, in principle, we can go through the same procedure of integration and calculate that value, but turns out there's something much simpler. See, z is the difference between x and y, and negative z simply the difference between y and x. Now, x and y are independent and identically distributed, and therefore x minus y has the same distribution as y minus x. So that tells us z and negative z have the same distribution. What that means is the distribution of z now must be symmetric around 0. In other words, if we know that the shape of f of z below 0 is something like that, then the shape of it above 0 must be symmetric. So here's the origin. For example, if we were to evaluate f of z at 1, well, this will be equal to the value of f of z at negative 1. So this will equal to f of z at negative 1. Well, with this information in mind, we know that in general, f of z, little z, is equal to f of z, negative little z. So what this allows us to do is to get all the information for z less than 0 and generalize it to the case where z is greater or equal to 0. In particular, by the symmetry here, we can write for the case z greater or equal to 0 as lambda over 2 e to the negative lambda z. So the negative sign comes from the fact that the distribution of f of z is symmetric around 0, and simply we can go back to the expression here to get the value. And all in all, this implies that f of z little z is equal to lambda over 2 e to the negative lambda absolute value of z. And this completes our problem.